So I'm going to talk about what is the emergence, and still I don't understand what the emergence is. And then, but I have been in this field of artificial life for 30 years, and then still, try to understand what causes emergent phenomena. And then also in terms of artificial life, we say open-ended evolution. That's one of the key issues that we have been seeking for. Oh, by the way, so Happy New Year, 2008. So because this is still, it's 8th of January. Yeah. So first of all, my background and then my current field is artificial life. Although my background is statistical physics, but I have been doing artificial life for more than 20 years. And then artificial life is all about theory of brain and evolution. Because nobody have ever seen evolution, right, in real time. And then we don't understand what consciousness is by opening up the brain, right? So these are something that doesn't exist in reality, but we have to use it to understand how the evolution takes place and how the brain works. And the key concept that it's kind of obsession of artificial life is to understand open-ended evolution. The definition of open-ended evolution is pretty much depending on who is talking about open-ended evolution, but it's more like a constant ability to constantly producing a novelty. So a new kind of property emerges constantly. Well, only the example that I know is major transitions in evolutionary biological evolutions from the proto-life to life, and then also single cell to multiple cells. Also the emergence of sex, emergence of language. All these major transition is what we call emergent phenomena. But we don't know how we can understand the single system like evolutionary dynamics, if it exists, that can constantly generate novel behaviors. And that's, I think, one of the key issues here. Right? To understand the emergence is to understand what is open-ended evolution and what's the key issue behind evolutionary processes. So this is the overview of artificial life history. I have been putting up when I gave a keynote in UK 2008. Then there was artificial life has big 4 branches, starting from cybernetics back in 1960. Do you have any point or something? So this one is starting from gray water. It's making a small robot to understand how the living system is moving around and perceive the world. So this is starting from gray water in 1949, and then Breitenberg and all these virtual robot has been the major field of artificial life. Including Luc Steels and then Stefan Olpi and Dario Floriano. They have been doing evolutionary robotics. Now it becomes a very common strategy to understand robotics. But at 2000, there was very, very new techniques that we try to understand how to design robots, but we don't have to do it manually. But the genetic algorithm can evolve the circuits and sensors and connecting to the motor output. So that's what we did. And then, so this one is starting from Alan Turing. Then we call it reaction diffusion equations, and we've been studying how this patterns and structures emerges by just a difference of time scales of diffusions of reactants and activators, and also spatial structures. Right? That's the stream from Alan Turing. And then John McCaskey and Norman Placido, those my colleagues, they started a Proto-Life company in 2008. After 5 years, unfortunately, they failed to maintain this. But now Norman is still keeping this institute in San Francisco and try to understand how life emerges from scratch, what to say, yeah. And then the another one is, so this is more like the real chemical reaction diffusion equations to the real test tube experiments. And this one is von Neumann's idea. Von Neumann, in 1966, he invented the cellular automata that shows self-reproduction. So self-reproduction has been constructively proved to be true, that you can actually make a self-reproducing machine on a computer, right? At that time, that nobody has ever succeeded in making a self-reproducing system even with chemical or anything, right? But von Neumann himself mathematically proved that is possible theoretically with the computers. So from von Neumann, there's a economist, the game of life, Stephen Wolfram's cellular automata, and all these streams came out. So the last branch here is more philosophical concept of what is life and what evolution is. And one of the most characteristic feature of artificial life study is that there is a philosophy behind. Nobody wants to talk about philosophy anymore, right? Back in 30 years ago, the paper always started with some nice ideas of concepts of philosophies, but these days it's more like a technical reports, right, everywhere. But artificial life is very special. That we try to talk about what is life. It's not just the materials, but we have to think about what emerges on top of it. That's why this concept, this conference, its topic is going to be the emergence. So starting from Gregory Bateson and Francisco Varela and Rob Rose and also these days Evan Thompson and Ezequiel Di Paolo, and all these people have been talking about philosophy of life, right? At one of the conferences that I went, he was a specialist in biochemical processes, and he talked about the details of biochemicals, and he said, "Don't ask me what is life or what is consciousness, because everything is totally understood in detail. But if you start to ask me what is life, and then nobody can answer it, right? So assume that there's no life, there's no consciousness." That's what his answer, right? Yeah, I know this is the easy solution, because if we don't have any life or consciousness, the problem is so easy, right? We have to go. But that's what artificial life exists. On the other hand, this top three, the Philogeny, is up to 2008. So I think there is a big revolution of scientific technologies and concept in 2008. So before and after 2008, everything has been changed. So I had to change my way of approaches, not in artificial life, but many other fields has been facing with this revolution, I think. I don't know whether you are aware of it or not, but I was strongly aware of this transition in 2010. But now, after these transitions, there's a synthetic biology. I mean, after this reaction diffusion equations has been studied, the people are switching to synthetic biology. So you don't have to do the interesting phenomena, try to have the interesting experiment in computer, but you can use a test tube and do the minimal evolution processes in the test tube. So that's a big change. As you know, starting from gray water, that now we have a Boston Dynamics, right? Everywhere on YouTube, you see a fancy robot, right? And that's big differences. I don't know whether you know speculative realism. That's a very pop now in the United States. And then this one is basically that we shouldn't make equations or model based on what we see, but the reality is something different, right? We have to expand our spatial temporal scales, and that is what we need to model, natural phenomena. But I'm coming back to those issues. Today, I'm going to talk about what happens after von Neumann, and then I'm trying to understand the recent approaches to this, by using those ideas. So the first of all, I have to say that what I think about emergent phenomena is, right? So usually the people, I think, are confusing with the idea of self-organization and emergent phenomena, right? Usually the people can have self-organization but cannot have emergent phenomena, because self-organization is more like you have a bunch of particles producing macro phenomena. That's the self-organization, right? But we really rarely call it emergent phenomena, because the emergent phenomena needs sequential repetition of self-organization. Once this one happens, and then again, the next one happens, and then the next one emerges. So this sequential emergence of self-organization is necessary to understand why it happens. Right? And almost 99% of artificial life models is preparing the lower level and then creating the next level. But that's it. It stops. We don't know why it cannot keep going on and on. But it's always, preparing the lower level and then creating the next level, and then it stops. So the question is how we can make a third one or fourth one or fifth one and constantly generating a new kind of structures. And I think nobody has ever succeeded in doing this, and we don't know why in evolutionary systems can show this, and then also human technology can do this, right? So maybe brain is necessary to do this, or maybe something is necessary to have this sequential repetition of self-organizations. So that's my definition of emergent phenomena here. So the question is, what are the necessary conditions for creating emergent phenomena? I think I have three difficulties for the moment that why you cannot have this open-ended evolution or emergent phenomena. What I think. The first one is we need a large spatial scales. We still have very few numbers of particles that we can deal with. And for example, like the numbers of Avogadro number, it's not unreachable. It's almost there, right? But with supercomputers or K-computer, one Avogadro number of the particle is difficult to simulate and see how the system behave. So it's one of the first things that we have to think about is we have to simulate a large number of particles or very detailed hierarchical structures inside of the system. So both of them is lacking. So if we have a huge number of particles or very detailed structures, fine structures, then maybe we can have a emergent phenomena. We don't know, but that's one of the criteria that we have to think about. For example, like do we need 100 billion numbers of neurons to have a brain system, or just 100 neurons is easy and then easy manipulatable to understand brain functions? But we cannot answer to these questions. But second thing is deep evolution. So evolution processes takes 4.6 billion years. So maybe we need a very, very long time to have an interesting phenomena to come out. And then usually we think it is impossible, right? But one of my colleagues, Lenski in Michigan University, that he has been doing this like 30 years, like E. coli, and then once he saturated the population numbers, then putting into another flask, and then doing this for 30 years. Then finally he found some single branches, a new kind of phenotype emerges like 10 years or something. So he's one of the pioneers that actually he tried to do evolutionary processes by his hand, right? And then he's clever, so because you cannot, catch up him once you start today, but he's always 30 years ahead, right? So this is so difficult. Even if you can parallelize your experiment, but still you cannot accelerate evolutionary processes. So one of the motivation of artificial life is how to accelerate evolutionary processes. If you can do 4.6 billion years in 30 minutes, that's wonderful. But of course, we don't know how to do this, right? That's one thing, the second thing. And third thing is the choosing the right initial state. That's always the big problem. Or maybe the self-organization does work. So usually the people think after 1960 or 70 that life phenomena is a self-organizing phenomena, right? However, if it's self-organizing phenomena, that should emerge everywhere, right? But it's so difficult. It's so difficult to do it in experiment in the laboratory. Means that probably life is not self-organization. It's something else, because we really have to carefully design initial configurations. Otherwise, we cannot have a life phenomena. So I think the self-organization is a misconcept that we have to replace it with something else, but we don't know how to do this, right? So these are the three things. And I have one of the crazy thing that so maybe you guys know this, but so this is Peter and David's the way things go, right? You know. This video takes like 60 minutes, so we don't have to. But of course, the question is, if the evolutionary processes is like this, you really have to think carefully, right? There is no one single equation that describes the evolutionary processes, but you really have to think in each processes and how it's connected to the others, and next one comes. So there is no such unified theory or unified equation that can describe the entire evolutionary processes. So that's also my worry, and then I don't know if this one is true or not. So, but we believe that there is only one universal laws or something that governs the biological evolution from simple chemical reactions or messy chemical reactions to human beings. Okay. So this is the third example that I think. Do we need a right initial state or right orbits to connecting one from this? So this connected orbit is necessary to understand what the evolution process is. Or maybe there is another kind of self-organization that works, and then we don't have to worry about the initial state so much. That's the thing that I want to discuss. Okay, so coming back to the revolutionary processes in 2008, I think these are three classes. I don't know why accidentally it happens at almost exactly the same time of the year. In 2008, there's a Rubik cube, De Broglie's speech form, what the Keller's reconstruction, the lattice development processes. These are the big data that have been reported in 2009. And then, of course, deep neural network, deep learning is studied from Jeffrey Hinton's paper in Deep Network in 2007. And also Satoshi Nakamoto's blockchain as the Bitcoin's background theory. I don't know whether he exists or not, but this idea also came out in 2008. It's a software. And hardware is a software, and then hardware is iPhone 3G. 2008, we didn't have an iPhone. It's so unimaginable, right? So after 2008, everybody has iPhones or Android or anything. And then also at the same year, there's an automation science was published by Ross King. That's another paper that you can automate everything, right? Not just making a chemical experiment, but making a hypothesis and updating hypothesis automatically in a single machine. That's possible. So this one changed the way that we think science, and then we have to change the way we understand phenomena. I can just, there's a beautiful TED talk by Deb Roy, so you can go and see TED talk by Deb Roy. But the interesting, I was so knocked out by this Rubik cube because I love this. I think everybody knows Rubik cube. Okay, I think. So until 2009, that everybody believes that we need 22 moves at the worst case, that we have to turn 22 times to reach the solution. Means every face has the same color. Right? However, so mathematically, it's proved that 22 is the upper bound of the worst numbers of the manipulations. Right? However, one of the Google guy, he heard about the Rubik cubes, 22nd number, and he said, okay, I can try that. And he used like many thousand computers at the same time, and then after a few weeks, he discovered, okay, that's a 20, right? So everybody was so surprised because mathematically using a group theory that we know that was 22, but this one was a 20. And then what he did was, Avogadro number is 6 times 10 to the 23rd, and then the possible numbers of combination is 4.3 times 10 to the 19th. So it's 10,000 Avogadro number divided by 10,000. Right? So, well, this number is not so big, after you have GPUs and huge numbers of computers like in Google. Not in universities, but Google can do this, right? And then, so the people are very surprised that, even the one researcher, he used thousands of computers at the same time, and then also he reported his this result not in the journal papers, but in the blog that he put on the blog of Google and said, "Okay, I solved it 20 times." And then there's no solution, there's no algorithm, but they just use the computer to make a big table, right? And then see what if first of all here, and then goes to there. So you don't have to have any group theory or beautiful mathematical equations or anything, but just a big table. And then there's a search algorithm that you can just search very quickly and then can solve the solution. However, this one is called a God algorithm, right? So if you have ever experienced in solving a Rubik cube, that you have to visually have to, first of all, looking at the corners and then put the same colors here, right? And then surface here. So because we have so much visually driven living system, right? However, the computer doesn't have views, right? So this one is more algebraically solved. So once you solve how he solved the problem, it's more like randomly changing, and then suddenly there's a solution is reached. So that the people call it Gauss algorithm, because human cannot understand how to do this, but only the computer can solve the problem. So what the revolution of 2008 is that I think human is the bottleneck, right? For the science, we don't need any human beings to understand, because we need the equations to understand what's going on here, right? But equation is not necessary for the big program to understand the phenomena. From big data to big data is necessary, and then equation is just bypassing, because human cannot understand this big data. So we have to write down in equations, and people are so happy. Okay, so I know this equation is right. However, this is already it's approximations. Once we want to use this equation, that we really have to make an approximation and put it into the computer again, right? Also, the visualization is not necessary. The computer doesn't have eyes, but the human beings has to visualize the data set, right? But from the big data to big data is necessary to understand what's the flow is. So visualization or writing down the equation is always a bottleneck. So maybe after 2008, we really have to think about what's the meaning of understanding the phenomena, right? Understanding phenomena is not writing down into the equations or reducing the data set into the thing or the visualizing into the 2D or 3D. But we have to understand complex phenomena as it is. The complexity shouldn't be reduced to something, but there is a way to understand the complex phenomena as it is. But that's one of the motivations for artificial life and then complex systems in general, I think. So, so after 2008, I tried to use the old model to understand what happens if you can increase the spatial scales or numbers of the particles. So that's one of my trial. So Craig Reynolds in 1987 he made a simple simple Boyle model. It's how to simulate the flocking behavior by simple rules. This is the separation. So if the agents are coming too close to each other, they're separating from each other. Their heading direction is aligned, and also its cohesion is that they try to come each other. So attractive forces, repulsive forces, and then also alignment. And with some, this is the view direction. This is angles and this is distances. So there's 9 different parameters, but using this equation that you can see some interesting flocking behaviors, like this one. So you can have a Torus behavior with this one is number 256 particles. This is, for now, it's easy to simulate numbers of 256 particles, but after 30 years ago, it's always difficult, right? Even 1,000 particles is difficult to simulate. But now we have GPU, and then also I can use a K computer to simulate a massive number of particles. And so one of the questions after 2008 is what happens if we increase the scale, even with the simple systems, whether the behavior changes or not. So this is the 2048. This is the periodic boundary. So this guy goes this way and then coming back from here. I know this is very strange boundary conditions for 3D because this one goes this and coming back here and goes this way and then coming. So it doesn't exist in the world. And then this is the 116,384. So it's even the same parameter set with the same density. So it looks like same, but the space scale is expanding in order to keep the density the same as in the small numbers. And this is 130 hundreds, thousands of particles. So it's more becoming more dense, and then the behavior becomes different. So this is 500,000 particles. So again, I thought I said this one is the model for flocking behavior of the birds, but it's no more birds, right? It's something quite different. Actually, when I gave this talk in front of in Annual Physics Society, and unfortunately, the people sitting in front of me was studying birds. And after my talk, that he raised his hand, and this is not bird. But anyway, so this collective behavior is only possible when you have high computer systems, so high-speed computer systems, and this is the current. So this is the current version of this simulations. So the big one is front, and then the smaller one is behind, right? Because I was asked that why there's big one and small one. But this is a 3D view, right? So it's starting from the scratch of the positions and directions, but gradually making some structures, right? And actually there's the big blobs, and then some streams of the birds is connecting from one to the other. So that's what you can see, like 1 million birds, So this is not the 256, but just increasing the numbers with the same rule set, with the same density, but just increasing the numbers of particles. And you can see gradually forming something. One of the interesting point is that those flocking behavior is no more independent from each other because it's always connecting through some small tubes, small streams of the birds, of the particles. And then, so I was, this is one of the things that I was surprised because I didn't expect this kind of systems emerges after, after run those particles in a K computer and then, download in my data set and then try to visualize because we have to visualize to understand what the big state is. Then this is what happens. So in order to analyze this one, there are things that we have to do. First of all, we have to clustering them, right? So it looks like there's a swarms and connecting, but it's so difficult to label different flocking behaviors. One is this one, or those small ones, and these orange ones and yellow ones. So that's what we use a bunch of different types of techniques using deep learnings or DB scans or all the other stuffs to label different ways. And then also the most difficult thing, if you have experience, in doing clustering of this kind of thing, you can please advise me how to do this. Because first of all, it's a dynamically changing, right? So if you have a snapshot, and in order to cluster from each time step, same flocking behavior is labeled with the different colors, right? In order to have a continuous labeling and coloring the same flocking behavior, it's difficult. Well, we have some solution to this, but still it's not complete. So I just need to do this. And then one of the things that we found was that there is a clustering not in a the big method, the important method is how to define the distance between particles, right? It's not just a real space, but we also have to use the velocity space. So 6-dimensional space to define distance. Then we can see that these blue ones and green ones are different. And I don't know whether you can see this. So this green one on the surface of the flocking behaviors means that the surface of the particle is much faster than the inside of this flocking behaviors, right? So when the particle comes to the surface, then speeding up and then making a new clusters and then bifurcating, right? Even if the same rule set, there's every particle has the same rule, following the same rule, but still the behavior is bifurcating. Some fast ones, slower ones, and then different kind of flocking behavior emerges. Because of this modeling that we are bounding the velocity in between this one and this one. So these are the particle. The slowest one is here, and then the first one is here, right? So the slower cluster is always like a big one, and then first one is class with like a snake-like flocking behaviors. These ones are always coming out from the surface and then connecting to the others. I think one of the most interesting thing is that by increasing the size of the each flock, so it's a 10,000 size flocking behaviors, the kinds of fluctuations becomes different. The smaller ones has fluctuations in direction, speed directions, heading directions, right? So the smaller ones has the more has the fluctuations in the velocity directions, but the larger flocking behavior has the density fluctuations. Number density fluctuates. I'm not quite sure why it changes, but that's one of the big transitions that, after like 10 to the 2 times or 3 times to the 10 to the third to the 10 to the fourth, the kinds of fluctuation is shifting from different fluctuations. Means that if you know this fluctuation theorem, that once you perturbate the system, the response is coming from this fluctuation for the smaller ones, but density fluctuation is responsible for the large flocking behaviors. And then also the information is mediated by the speed or the fluctuations as the first approximations of the Navier-Stokes equations, right? So information is carried by the heading direction of the fluctuations to density fluctuations. That's the transitions that happens here. So this kind of behavior is simplified by the Vicek in 1995, and he defined the order parameters of this flocking behavior. And then the flocking behavior is simply just summing up all the velocities of the system, and then once you increase the numbers of the particle, there's a sharp transition emerges that you can see. There's a transitions, but the Vicek model is there's no repulsion or attractive forces, but just alignment of the directions with neighbor particles plus some noise added to the as a second term. And this one, by increasing the noise or decreasing the noise, there is a phase transition emerges in 2D space. That's what Vicek's idea. And then when you look at, so this is almost like a Vicek's, so this is the velocity. So the Vicek parameter it goes almost zero for the large flocking size, but it's very high for the high speed system, lower flocking behaviors. So the big ones and small ones exist. So the order parameter is zero for the big ones, but order parameter is non-zero for the smaller ones. That is coexisting in the same systems. So it's more like, even if the system is huge, but the order parameter is distributing in the whole systems. So that's one of the interesting things. The big ones, the order parameter goes to zero. However, the fluctuations of the numbers of the bulk coordinate density goes up. So there's a transition from the this size of the flocking behaviors. So that's one of the discovery that we have found because of this large scale simulations. Also, we looked into the flocking behavior and then using non-negative matrix factorizations and how the particles are committing to this breakup of the large flocking behaviors. The non-negative matrix factorization is this is the time, this is the level of the each individuals. Then we can decompose by using product of two matrices, and then we are adjusting those numbers of the columns, the length of the columns by minimalizing Kullback-Leibler information criterion. Then we see that so basically this is more like eigen behavior of the flocking behaviors. So big one is coming up, and this is called this. So once the big flocking behavior is breaking up and then sticking out those small but non-zero Vicek order parameter behavior is emerging, then that's why this first mode is coming up. So this is something we still analyzing those kind of behaviors, but the huge one, we cannot understand what's happened there, right? Because the high dimensional dynamical systems without noise. So one of the techniques to understand the behavior is using a non-negative matrix factorization to see what kind of mode is interacting with each other and break up the big ones. So this is the first one. If I don't know how much time, go ahead. 10 minutes? Okay, 6 minutes, it's fine. So the second one is a Gatchis model. This is an interesting paper published in 2001. And this one is, as you see, is 200 pages, right? This is crazy. I like this paper because it's 200 pages, right? These days it's like 8 pages or 10 pages, but this one is 200 pages because this paper is about how to have a robust one-dimensional cell automata. And then behind of this paper is that the positive rate conjecture that one-dimensional faulty cell automata with finite interaction neighbors, strictly positive error rate, and strictly positive noise distribution can have at most one stationary measure. That's the criteria. But this paper refute this conjecture. There's a bunch of different types of metacellular cells can exist, even with the finite range interactions with the one-dimensional cell automata. So this conjecture says that there's no phase transitions in one-dimensional space if this interaction is finite. However, Peter Gatchis showed by making a special cell automata that this one is not true. And an interesting idea behind it is that hierarchy of majority vote on the contact processes is epidemic processes like diffusing epidemic point is to correct errors. Even if the site is flipped accidentally by noise, you can correct it always, right? And then the paper is very strongly say that any strength of noise can be corrected by this rule. And then one of the very interesting techniques that high-order operations are made possible by self-simulation. So it's self-simulating cell automata. So each site is always, simulating what happens in a different spatial temporal scales. So one of the idea of the Gatchis model is that this model is capable of universal computation and can be implemented in continuous time. So people are criticizing because it's discrete time, space-time state, but they can translate it into a continuous time. And also can be made a self-organization. So you don't have to, indicate something, but once given the initial figure configuration with the rule, that you can self-organize. And this has a positive capacity property, so that the hypothesis has been negated. So the most hierarchical constructions, including this one, start from complex hierarchical initial configurations. But Gatchis, this model avoids this by having a couple of transition rules. So you don't have to worry about the initial configuration because this rule set is correcting and then coming back to the same patterns. So I can quickly going to the, this is on the 150 pages, so I cannot condense within 3 minutes. But one of my PhD students, Lana Schnapperian, this is one of my obsession that I wanted to simulate this one because nobody ever seen how to simulate this. But Lana came to me and then she can do it. So we've been discussing whether this is possible or not. This is the first part with the noise, lower noise part is rather easier than the high noise part. So basically we simulated by the lower noise part of the cell automata. But one of the ideas is that the cell automata has a colonies, right? Each colony has a 127 sites, and then one of those, if it's small errors, then we put the flags on, right? And then if the flag is on, that try to mimic the left-hand side of this side and then try to correct it, right? That's the lower noise part. But if the noise is too high, then we renormalizing all the colonies, and then 127 site expresses one state of the single cell, right? So renormalizing all the colonies, and then each colony expresses one state of the cell of the next level, right? So the renormalizing cell is 127 larger than the original one, but then this one can simulate the lower one's level, right? So if you can refer to this renormalized space, that you can correct it. But the error is much larger than this, then you can always go to the next level, then renormalizing again the cell. So each colony of the colony can express the single cell of the first layer, right? So you can simulate a renormalized cell to correct the original cells. That's the way that you can correct. So this is the level 0, and then this level 1 is expressing single cell state, and then go to the level 2, and then again you renormalize it, and then expressing the third one, right? So this one is a hierarchical ordering. So each cell has not 0 or 1, but numbers of the state is 2 to 230. So it's more like each cell is a computer. Its computer is connecting to each other. But this one computer is trying to express one bit. This is such a stupid computer because it's so bad cost performance. But still, this one is error robust. It's a very, very robust server automata. So this is how it works. So if the error is small, this is error 0.05, and this black dot, the black point is where the state is flipped, but then is collected afterwards. And this one is error 0.5, then still the error is huge, but they can correct after. So this red line is that after this, the error noise is shut down, and then system goes back to the original state. But once noise is larger than 0.6, this one cannot correct the noise. So this is one of the simulations that we did. Those are the colonies. Then after those random noise is added to the system, but then after noise is shut down, that they can coming back to this the original state, but still a bit shifting to the right side, hand side. Okay. Yeah. Yes. Yes. And this is how the simulation does look like. Yeah. So this computer simulation is possible with this high-speed computer architectures with Lerner's supercomputing programming techniques. So this is how the system can be recovery rate versus error rate. So the discussion part is that, so this is the final page. So I think the large number of agents problem can be solved by the progress of computational power. I know this is very too optimistic, but the large void simulation demonstrates that the transition from the small to large swarms means the transition from a non-zero big check order parameter to zero state and a coexisting of it, right? Maybe this can, so each superorganism emerges after 2-3 order differences. This one is a million numbers of the birds. After 1,000 times larger than the million birds, maybe there's another structure might emerge. Like our cells, right? We have cells, our bodies, and societies. These are superorganisms, and scale is almost like 3 orders differences. So we are expecting that maybe expanding the spatial scale, emergence can occur by just increasing the particle numbers. And the second one is maybe the power of the individual structure per site enables the new macro orders. So not just increasing the space, but going into the details of the scale, like a Gachis model. It's a 2 to 230 states per site can help the system to become robust and can have more evolutionary power. So even like a spatial extension of details, fine structures. Now that this high-speed computer is possible to do number 1 and 2, that's maybe I'm a bit optimistic, but that's one of the way to solve the emergent phenomena by using this computational power to searching for the large scale spatial scales and also fine spatial structures. That's something I'm doing now. Thank you very much.
Okay, so Selena's going to set up this question, the Slidos questions, and then but in the meantime, while he's getting set up, is there a question to start the discussion from the audience? Lindy.
This is a scary item that you just handed me. That's great, I know. Really, really wonderful talk. I'm just particularly interested, going back in the talk a little bit, to the flocking bird discussion. I wonder if you've made progress in understanding the differences between your flocks and bird flocks. That's such an interesting question.
Well, so do you mean like I can understand something in a real world by my simulations? Yeah, I think that one of the parameters that I was adjusting is that I think usually the people take an infinite limit of the numbers of the particles, right? But the large numbers of the particles is necessary to understand the Burst phenomena. Not like hundreds or 1,000, but 1 million, all these kind of orders is maybe there's some new kind of physics or new kind of phenomena exist, but it's difficult to understand this one, right? So usually the people take a thermodynamic limit or hydrodynamic limit. But if we don't take the infinite limit but stay there, then maybe there's some new kind of phenomenon like a finite scaling phenomena. Like coming back to the one of the philosophical questions recently that people have been discussing, like a new kind of philosophy, is that don't use any sort of the particle that we know, right? But the spatial and temporal scale must be extended from the. So one of the most advantages of using internet or high computer is that our perception of a spatial and temporal scale is highly extended. It's not linearly extended, but exponentially extended. So maybe the Burst phenomena, even if it's simple, but still we cannot understand in a simple way. But maybe we need a large number of phenomena is to understand it, right? But one of the disadvantages of this one is each particle cannot understand which flock that they are belonging to, right? The perception of the void is necessary. So I've been doing with Olaf Witkowski that each particle has a neural network inside, and how those neural networks can evolve by making flocking behavior is something that we've been working on.
Okay, let's go for a question here that was submitted by on Slido. One is by Nathaniel Virgo. It says, Turing's original UTM had many states, but now we know there are UTMs with just 3 or 4. Do you think the same is true for CAs with gaseous property? This one here.
Oh, this one, okay.
Yeah.
So there's a very short character when you say that.
Ready?
So Turing's original universal Turing machine was kind of hand designed, and it was really complicated and it had loads and loads of states. But people like Stephen Wolfram have done exhaustive searches, and they found Turing machines with the same property of being a universal Turing machine that had only a few states, like 3 or 4. So much simpler systems that have the same property. So I'm wondering if you think the same would be true for CAs that exhibit the properties that the gaseous model has. Like maybe if you were to find the right ones, they wouldn't need to be nearly that complicated, and it would just happen naturally.
That's a very, very interesting question, but of course I don't know that, right?
Right.
I'm afraid that, first von Neumann's model has a 29 state, right? After that, the Japanese people are coming, okay, you can make it like a 10 states or small state. So Japanese people are good at, lowering the numbers of states. However, I think the essential parties cannot be different. And also, an interesting thing with the Gatchis model is that his idea of using self-simulating capability of cell automata, right? Maybe the brain system is using a self-simulating capability because of this robustness is supported by self-simulations, right? Maybe the cerebrum or this. So I think the idea is interesting, but the way to implement is I don't know whether that's so important or not.
Mm-hmm.
But maybe you can solve this problem, but not me.
Okay. Thanks.
Any other questions from the audience? We can also go to the next question. If you have any question, raise your hand. So let's go to James.
So just as a point of clarification, so even Claude Shannon realized that there's a trade-off. For universal Turing machines, you can reduce the alphabet size for the cells on the tape, but then that increases the number of states in the finite state controller. Mm-hmm. And so people have studied there's a kind of a inverse relationship between those two things. Yeah. So even if you simplify one aspect of the implementation, in a sense your programming or implementation costs go up in some other dimension. Mm-hmm. And no one wants to program a universal Turing machine anyway. It's god-awful.
Yeah, you're right. Well, actually, this 150 pages of the paper is all about inventing a new computer language, right? How to complexing and how to express. So that's why this takes 150 pages, because it's all about the new languages, right? And the first 50 pages is comments from reviewers of the paper, right? Because the reviewer didn't understand it, so they stayed in a single cottage for 1 month and writing a paper together, and then 50 pages becomes the introduction. Yeah.
So we have 2 questions from David.
I thought everybody was putting tons of questions in, so I was doing my best. So can I just whittle it down to one thing? So this is coming at this a bit naively. I guess I always had assumed that the concept of emergence was something that was basically about being able to make efficient predictions, because you can look at a whole, you don't have to predict. So I think the second one, maybe the most relevant one. So in your swarms, it seems to me that you would want to just have when you cluster birds into swarms, does your algorithm know what all the birds are doing? Because if it does, that seems to cheat. It feels like you should look at take basis on the basis of density, cluster, and then ask the question: how much data can you make an efficient prediction that you would be very difficult to make? You need much more data to do it by doing the whole simulation at the level of the birds. Is my question clear?
So you basically you're asking whether we can do more clever algorithm to simulate this one by using this?
Well, I guess I'm asking, the question of is there emergence suggests that you could do something just by looking at the swarms, even if you had no underlying model or knowledge of the birds, and that your predictions wouldn't be perfect, but they would be much better than they would be if there was no swarm formation. And I'm asking if that's actually, what emergence is about, or maybe I'm missing something about the concept.
No, I think, one of the ideas is that some of the flock is more energetic and more healthy than the others, right? And all the properties is intensive property of thermodynamics. Well, thermodynamics is all about, without looking into the details, but you can still, if you have an extensive value, then there's an intensive property that are associated with the extensive thing, right? So the swarming behavior, I think it's a pseudo or conservative system, so that they don't have any temperature or anything, but they have a conservation of numbers, or some flocking behavior can exist for a while. So maybe there's some extensive value. So associated with it, there's an intensive property of the swarms, I hope. So using this, maybe I'm trying to do this, but it's difficult to do this. But maybe there's a thermodynamic way of describing the systems. And these now we know that thermodynamics is introducing information capability, information values as a thermodynamic value into the so we call it information thermodynamics. So maybe that's also possible to describe all this flocking behavior to predict what new things came out, or it's kind of new formalization of flocking behavior. I don't know whether I could answer to your questions. But in other ways, we know every micro state of the particles, right? But we don't know how to use all those data to predict what's going on in a scales, right? The large scale, the numbers of particles is also the parameter of the system. So that's why I don't think we cannot predict, even though we know every details of the particles, but we cannot predict what happens in the macro level, because the numbers of particles and space itself is a parameter. I think it's for the system, like a neural network. Each neuron is a parameters, and the numbers of the neuron in a single layer is a parameters. So it's a state and parameter is indistinguishable for this large system. That's why I think it's difficult to predict what's going on in a macro state.
Okay, so let's thank Takashi again for this very stimulating talk.
Okay, thank you very much.